Our next video for Unit 3, we have learned how to take the first and second derivative. We applied the first derivative test for extrema. We used the first derivative to determine increasing and decreasing. We are going to be moving down here, which is using the extreme value theorem to determine if a function has an absolute maximum or minimum. So, by definition, all right, we're going to start both these definitions for a maximum and a minimum by saying that we are given a function h, well, h of x, right? X is our input, is continuous. So remember, completes all three pillars, can draw without picking up your pencil, on some sort of interval from a to b, and c is an element of a to b. So c is somewhere on that interval. Then h of c is the maximum of h of x if h of c is greater than or equal to h of x for all x that's on the interval from a to b. Now, what that means is that this y value, h of c, is greater than or equal to all of the other y values. Basically, the tallest in the room, right? H of c is the maximum if it's the tallest output. Well, similarly then, a minimum on an interval, h of c is the minimum of h of x if, this time, h of c is less than or equal to h of x for all x on the interval from a to b. So this time, h of c is less than or equal to. They're the shortest in the room, if you will, when comparing to all other heights of the function. The extrema, you might remember this from last time, x is where? Y is how tall or how small. So when we ask for the value, we're looking for y. When we ask for the where, we're looking for the x. All right. So the extreme value theorem, often abbreviated as the EVT, right? We've already had the IVT, now we have the EVT. This is supposed to read as dun dun dun. I don't know if I really get that from that typed da-da-da, but whatever. If h of x is continuous, on the interval from a to b, then h of x will have at least one maximum and at least one minimum. So let's break this down a little bit. The first thing is that our function has to be continuous. All right, if we have a discontinuous function on our interval, this theorem does not hold anymore. The next thing is that our function has to be defined on a closed interval. So if we think about, for instance, a parabola, right? A parabola is not defined on a closed interval. Its domain is negative infinity to infinity, and a parabola only has a maximum or a minimum, depending on if it opens up or down. What we're talking about here is a function that is cut off. We're looking at a closed interval from a to b. We will be guaranteed to have at least one max and at least one min. which means that you have a tallest person in the room and a shortest person in the room. The way we do this is what we call a candidate's test. A candidate's test is where we line up all of our potentially interesting x values. Well, our potentially interesting x values are going to be the endpoint A, the endpoint B, and then any critical numbers that we find in between A and B. And remember, those critical numbers are where important things are happening. They become candidates. They could be because f prime is equal to 0, or they could be because f prime was undefined, but those become candidates for where a maximum or minimum could occur. Then what we do is we take those candidates and we go back to the original function and we figure out what are all of these heights, right? And we'll compare which one is the tallest, which one is the smallest. All right, so here we have a bunch of math teachers. We have Mr. Covey, we have Mrs. Fry, we have Mr. Lakin, we have Mr. McConey, and we have me, Ms. Schwartz. Right now, we are lined up alphabetically. Covey, Fry, Lakin, McConey, Schwartz. So if I use this as my graph, I have absolute extrema for those that are the absolute. I shouldn't use absolute in the definition of absolute. It is the lowest or the highest on a closed interval. Well, my closed interval is going to be this set of math teachers. So from Covey to Schwartz. Our absolute minimum is going to be Fry, and our absolute maximum is going to be McConey. So Fry is like the input, right? Fry is where the minimum happens. 62 inches is the absolute minimum value. Whereas McConey is where the absolute maximum happens. 77 inches is the maximum value, inputs and outputs. Now, Mr. Lakin here is neither a max nor a min, if we continue to draw through there, right? Mr. Covey over here is a little bit higher as we continue to fry, but because he's an endpoint, he cannot be a relative min or max. There's nothing on the other side of him that would help justify relative min or max. Likewise, over here, I'm relatively lower than all the people to my left, but because I don't have anything on the right, I'm just an endpoint. And so is Mr. Covey. He's just an endpoint. All right, but now let's see what happens when I rearrange our math teachers a little bit. So I'm going to rearrange us by birthday. So I believe Mr. Lakin's birthday, I gotta double check something. I'm pausing this video. Okay, I confirmed. Mr. Lakin's birthday is after Mr. Covey's. I know they're both in March. Mr. Lakin is after Mr. Covey. Then I'm in April. Mr. McConey's birthday is in July. And Mrs. Fry's birthday is in October. Her birthday actually was just this Monday. Ah. Well, you weren't supposed to see that yet. That'll come back later. Okay. So if I look at this closed interval now, Mrs. Fry is still my absolute. Mr. McConey is still my absolute. Notice this time that Mrs. Fry happens to be at the end point. That's okay. Absolutes can be at the end point. But a relative will never be at the end point. And what I mean by relative is if you were to connect from Mr. Lakin through to me up to Mr. McConey, I am a relative minimum. I am relatively lower than the person to my left and the person to my right, but I'm not the absolute lowest. That honor belongs to Mrs. Fry. All right. So relative local versus absolute global. So relative is on a small or close interval. Absolute is on the full domain, which remember, our full domain when we talk about the extreme value theorem, will be a closed interval from A to B. All of the locations of relative extrema, the derivative is 0 or undefined for relatives. Okay, relatives happen at critical numbers. And that's it. They can happen at critical numbers. That's all we have. But absolutes, oh, I didn't realize you had to fill in the blank. The x values of these special points are called critical numbers from the first derivative. Absolute extremum can be at those critical numbers, but can also exist at the end point if we are defined on that closed interval A to B, because now the extreme value theorem is taking place and we would run a candidates test. All right, so let's see this in action. Locate the absolute extrema of the function f of x on the interval from -2 to 1. So as soon as I see this, I'm going to set up my f of x candidates test. This closed interval indicates I'm going to want a candidates test. I'm going to put -2 and 1, my a and b values. Now I need to go through and I need to find my critical numbers, either from f prime being 0 or from f prime being undefined. Take a second for yourself and find me those critical numbers. F prime being equal to 0 or f prime being undefined. Pause your video, come back when you have them. All right, so hopefully you found -1. Now we're going to take that -1, we're going to plug back into f of x, our original function. I'm going to flash forward a little bit for time. We would get -4, -5, and -1. So looking at these things, the absolute minimum happens right here at x equals -1, and f of -1 is equal to -5. The absolute max, which of these is our highest? Well, our highest is an output of -1, and that happens when x is equal to 1, f of 1 is equal to -1. So remember, the x is where something is happening. The actual minimum value or maximum value is what is the output, what is the actual height going on. All right, one more example. Entries for a contest are being processed at a rate modeled by P of t. We've got this closed interval from 8 to 12, which indicates to me I'm going to need a candidates test. At what time were the entries being processed most quickly? Well, that would be some sort of a maximum, an absolute maximum. So I'm going to start by time and processing. I know 8 and I know 12. I want you to pause your video and find me the other critical numbers. So remember, the other critical numbers will come from p prime of t being equal to 0, or where p prime of t is equal, well, not equal. P prime of t is undefined. So go ahead and try to find those two things. Pause your video. Hint, you may need the quadratic formula. What? Go ahead and find me those 2 times. All right, so p prime of t is this nice quadratic. This quadratic does not factor nicely, so I used the quadratic formula. I came up with these 2 values from my calculator. So now I need to take those values and I need to substitute them back into p of t to see what my outputs are. Well, p of 8 ends up being 0. P of 9.184 ends up being 5.089. You can check my math if you want. P of 10.816 ends up being 2.911. And then P of 12 is equal to 8. We're going to use 3 decimals for AP calculus, so thousandths place. Well, which one of these is the most quickly out of these P's? 8. But this question says, at what time? So at time t equals 12, entries were being processed the most quickly. So what's important here is that our maximum happened at an endpoint. This one back here, this we qualified as the minimum, this we qualified as the maximum. This endpoint is just an endpoint. That's it, just a sad, lonely endpoint. Nothing important about it, unfortunately. All right, we're going to come together to do a little bit of a wrap up and a few more problems, but here's a quick summary to jot down. See you soon.